Hello and welcome to Armagh Observatory and Planetarium's first ever online Startracker evening. We're sorry we can't be with you in person tonight, but we've decided to bring our Startracker online. So what have we in store for you tonight? Well, we're going to start off the evening with our operations manager, Martina Glass. She's going to guide us through what you can see in the night sky at this time of year. And you know what? You don't need one of these. These are objects that you can see with the naked eye. Following Martina's talk, our head of research, Mark Sarzi, will be telling us all about supermassive black holes. So if you have any questions on what is a black hole, where do they come from, put your questions into our chat during the evening. And also Martina and Mark will be available for any questions whenever our Facebook Live ends. Just put your question into the chat whenever the video follows. So to kick off this evening, we're going to start off with Martina and telling us what we can see in the night sky.
Welcome to our virtual tour of the night sky. As the sun sets, you will see the sky darken, the clouds drift overhead, and the stars start to appear. And if you can find an area away from streetlights, you'll be able to see lots more stars and maybe even some other celestial objects as well. Now, in this spring night sky, we're going to use a very familiar group of stars to help us navigate and find our way around the night sky. Any guesses what that pattern might be? Take a look out after sunset in the west to find the moon, Venus, and the star cluster, the Pleiades, almost in a row in the sky. So Venus will be the bright star-like object that you can see in the sky. It'll be much brighter than any of the other stars and it won't twinkle like the stars. The stars twinkle as the light from them gets interrupted travelling through our atmosphere. Venus reflects the sunlight back towards us, and because it's much closer, it appears much brighter in the sky. The moon will be in a waxing crescent phase, and we'll gradually see more of the moon as it makes its way towards a full moon on the 7th of April 2020. These days with light pollution, you're doing well if you can see about 5 or 6 stars in the Pleiades star cluster. A generation ago, they may remember seeing up to maybe about 14 or 15 stars when light pollution wasn't as bad as it is today. However, with a telescope, or like this stunning image captured by the Hubble Space Telescope, it reveals that there's actually over 1,000 star clusters in this one little tiny area of the sky. Now, in this spring night sky, we're going to use a very familiar group of stars to help us navigate and find our way around the night sky. Any guesses what that pattern might be? Well, this is the Plough or the Big Dipper, and we're going to use this pattern of 7 stars to help us find some other constellations in the night sky. So the Plough is not actually a constellation by itself. Instead, it forms part of a much larger constellation called Ursa Major, or the Great Bear. The Plough is something called an asterism, which is a familiar group of stars in the night sky, often making up part of a much larger constellation. If we follow the arc of the handle of the Plough and follow this arc downwards to a bright star, this is called Arcturus. So you can arc to Arcturus. And Arcturus, when it first appears in the night sky, it's a sign that spring has officially sprung. This is the brightest star in the constellation of Boötes the herdsman. This is the constellation of Boötes the herdsman. It looks a little bit more like a kite in the night sky. And again, we're going to return to this Plough pattern, this time using the 2 stars opposite the handle of the Plough and heading down towards the horizon. And we come to the brightest star in our next constellation. This is a star called Regulus. Any guesses what constellation this might be? It's one of the signs of the zodiac. It's quite a wild animal. So this is the pattern of Leo the lion, and Leo is a pattern that we'll see right through the springtime. In total, there are 88 constellations in the night sky. We've literally only looked at a handful of them here today. We hope that you have enjoyed this little tour of the night sky and have found it helpful. If you have any questions, feel free to comment, message, email, get in touch with us, and we will do our best to get all of your queries answered. So thank you for watching, and goodbye.
Thanks for that, Martina. I think we'll definitely be looking out for some of those objects in the night sky. Now we're moving on to our astronomy talk, and we have Professor Mark Sarzi with Supermassive Black Holes.
Good evening, everyone, and welcome to this Startracker online event. My name is Dr. Mark Sarzi. I'm the head of research at AOP, and tonight we'll be talking about supermassive black holes with the help of my little assistant, my daughter Morgana. Say hi.
Hi.
So, what are supermassive black holes? Well, supermassive black holes are basically like giant monsters that will eat everything that will come next to them and that lies at the very centers of galaxies. They do not form like normal black holes from the explosions of massive stars. They form, yeah, well, we don't yet know how actually they form. But before I can talk about black holes, I need to talk a bit about gravity, if you bear with me. How does gravity works? Well, gravity exerts a force between two bodies, and that force imprints an acceleration on a given body that is inversely proportional to the mass of the body. So I am that much strong, and with my same force, I can imprint an acceleration that is much stronger when I move a trolley in a supermarket, but I can really find it hard to push a car. I will make it move very slowly. So the acceleration, according to gravity, depends on the mass of the body that is attracting you, and is inversely proportional to the distance between the bodies. So this formula here actually is just to simplify matter, and it just refers to the acceleration that the Earth is suffering as a result of the attraction of the Sun. But the concept that I want you to take away is that this depends on the mass, and it depends on the distance. So if you go and put the Earth or twice as close to the Sun, if you go at the distance of Mercury, for instance, because you are twice as close, your acceleration actually will be 4 times as larger. Okay. Now the acceleration will make the planet fall, but planets do not fall into the Sun. They go about the Sun, and precisely they go into circular orbits.
Why do the planets doesn't fall in the Sun?
Well, I'm about to explain. They go about, and they go about the Sun at a given velocity that is called the circular velocity. So if you are Mercury, you have to go very fast not to fall into the Sun. But if you are Neptune, you can afford to be quite sluggish and go slowly. Now this velocity that makes you go around the Sun exactly in a circle is called the circular velocity, and depends on the distance at which you are from the Sun. Precisely, it goes according to this complicated formula that you don't need to remember. All you need to bear in mind is the shape of this curve that indicates how the circular velocity increases as you go close to the Sun. Now, this shape of this curve has a very well-known name, and I have a little question for you. Such a rotational velocity trend is generally referred to as a Ptolemaic curve, a Copernican curve, a Galilean curve, or a Keplerian curve. What do you think, Morgana?
Galilean curve.
What?
Galilean curve.
Ptolemaic?
No, Galilean curve.
Galilean curve?
Galilean curve.
I think you meant Keplerian curve, right? Keplerian curve is actually the right one. And that is because Copernicus, who discovered this trend back in 1619. Now there is another very important velocity that relates to the force of gravity and the acceleration that gravity imprints of body, and that is called the escape velocity. That is the velocity at which you need to jump out from the surface of a planet, or the Sun in this case, in this graph, to directly escape from that planet, to fly away if you are a rocket, for instance. That escape velocity is 600 kilometers per second if you're on the surface of the Sun, 11 kilometers per second if you are on Earth, so you really have to jump very high, and 1 meter per second if you are on the surface of a really a small escape velocity. So if you're on a comet surface, you really don't want to be doing jumping selfies, because otherwise you will just fly away. Now, how to make a black hole? How do you make a black hole? Well, as I said, the escape velocity, like the circular velocity, depends on the mass of the planet or body on which you are standing, and also on the distance at which you are. That is basically also the radius of the surface on which you are. So if you were to compress the Sun, the mass is the same, but the radius decreases, and so your escape velocity becomes higher. If you compress it twice, your escape velocity is 4 times as higher. So you can commit and then you have to go faster and faster to escape, and at some point your escape velocity becomes equal to the speed of light, and because you cannot go faster than light, you have created a black hole. Now a black hole has basically seen at the moment where you have compressed a mass enough, you create this virtual surface, okay? It's not a real surface, it's called the event horizon. So from that point on, you cannot escape the black hole. So if you're outside, you can really boost very fast and still escape. If you are inside, then basically you can't escape anymore. But that's not a hard surface, it's just a limit. It's just, a point in space. And to give you an idea on how small you have to compress object to make a black hole, is an example. So the sun, to make a black hole out of the sun, you will have to compress it into a sphere that is 6 kilometers across. And this is how we will compare, for instance, to the city of Belfast. Now, what about the Earth? Yeah, you're right. You could actually have your toddler to play with a black hole Earth. And when we talk about supermassive black holes, because these are, millions to billion times the mass of the sun, these guys have an event horizon, or if you want, their size is comparable to that of the solar system. Now, black holes are invisible by definition, so how do we even know of their existence? How do we spot a black hole? Okay, so here's another question for you. How can we directly, perceive the presence of a black hole? Through gravitational wave? When they accrete matter? Hawking's radiation? Or on TV? What do you think, Morgana?
TV.
On TV? Not true. We basically spot them when they accrete matter. We could also in theory spot them if they were, because they should emit Hawking's radiation, but we don't detect this yet. And gravitational waves, yes, they result from black holes, because they should emit Hawking's radiation, but we don't detect this yet. And gravitational waves, yes, they result from black holes, but from 2 merging black holes, not just one. So here's an example of what happens when you have a black hole that accretes matter. So this is in particular a stellar mass black hole, just resulting from the evolution of stars. When a star dies, the center part of the star can become a black hole, and that's one that actually is found at the center of this nebula, which is the Crab Nebula, which was an explosion of a star that occurred in 1054. And now that black hole is accreting matter here on this disk, which is very shiny and bright, and then it emits a jet here that goes out, and we see the jet in particular in radio or in X-ray light. The same happens around massive black holes, okay? So in galaxies, so that's the galaxy in the center here that you see, and on the left you have the X-ray light and the radio light instead of optical light, and in these 2 wavelengths you actually do see these jets that the black hole is firing out in space. Okay, so this is the way we know about black holes, but how do I know that black holes are supermassive, or they are this massive in fact? So how do we measure the mass of black holes? Well, to weigh a black hole, we need basically to feel its presence. We need to look with very, very big telescope, or with telescopes in space. In this case, I'm showing you the Hubble Space Telescope at the very center of galaxies, where we can see gas and stars responding directly to the gravitational pull of the black hole, which we can't see, okay, but we may see things moving about it as if there is something very massive that moves them. And this is exactly what happens in this graph. Here what you see is Hubble Space Telescope observation for the gas, in this case, in the center of this galaxy. So on the left you can see the dust and the gas is like a lane that goes around the center. And on the right what you see is a velocity curve of the gas. So in green is gas that is basically not moving very much, and as you approach the center of the galaxy, zoom, suddenly the gas goes very fast in one way. In this case it's blue, so it means that the gas is approaching us very fast, and then boom, as I go on the other side, the gas is moving very fast away from me, and then as I go away from the center, again the gas is going very slowly. And in fact, you may recognize this trend. We've seen it before. This is a Keplerian curve. It indicates that the gas is moving around something in the center, just like the planets move around the sun. So we cannot see what is it in the center here, but we know it's moving very, very big, because this gas is actually moving very fast, not just at some tens of kilometers per second, as in the case of the planets, but at hundreds of kilometers per second. So I mentioned that you can see, you can measure the mass of black holes with the Hubble Space Telescope, but sometimes you can do this also found using very big telescopes. So this is the European Southern Observatory, which consists of 4 8-meter across telescopes that can work together. So this is great. And then actually it's this telescope is at the top of this mountain, which has been cut flat, as you can see here. And this is actually the Residencia. This is actually in Chile, so it's a Spanish name for an hotel. This is where the astronomers sleep in the day after working at night. And sometimes we also have special guests, and we have a pool here where people can swim. Now, doesn't this start to remind you of maybe the set of a famous movie franchise? Which one? Harry Potter, James Bond, Star Wars, or Star Trek? What do you say, Morgana?
Harry Potter.
Harry Potter. That's not right, Morgana. This is a James Bond setting. In fact, Quantum of Solace was shot at this location. So how do you measure black holes with these telescopes? So we have to use a very special technique which is called adaptive optics.
What is that?
That's a telescope, Morgana. Just bear with me, okay, while I explain. So the problem of observing stars and galaxies from the ground is that we have the atmosphere above us, and the atmosphere makes the stars twinkles, and that's very nice for rhyming and singing songs, but the twinkling of the stars effectively decreases the sharpness of images that we can take, and this effectively limits how close in the center of a galaxy we can look with our telescope. And this is due to the fact that the atmosphere moves, and that by doing this, the light that comes from stars sometimes moves a bit to the right and to the left when it comes down to our telescope. A bit like when you are in a pool underwater, and you see, if you look at people outside the pool, at your mommy and daddy, or friends that wave at you, you see them actually, they don't still, the image is not still. And that's because the water is moving, and the light going through the water actually is deflected. And it's a phenomenon that is called as diffraction. So what I'm about to show you is a movie that shows you how we can compensate for the movement of the light as it goes through the atmosphere. So let me just zoom a bit further here. So that's a telescope, a big telescope, an 8-meter telescope. Here's the light is going through it. It's going to reflect it by the first, second, and third mirror, and then the light is directed into the special instrument that will correct for the blurring of the atmosphere. So here the light goes through the instrument, and the way the light moves is that, as I said, it's the star twinkles, and that's because the ray of light do not come parallel, or if you prefer, the wavefronts are corrugated. Okay, but if you want just to think about it, it's just the ray of light, they come and they move about. And so the key is to have this deformable small mirror that compensate and make the light go straight again. And when you do that, suddenly Here we go, the star is very sharp. Now, this in particular astronomers to measure the mass of the black hole in the center of our Milky Way, of our galaxy. So that's the Milky Way at night if you're in a very dark place. And if we zoom in, we can see some stars, and the image of the stars is quite blurred. If you look in the very center here, you probably make out only a couple of stars, but when adaptive optics is switched on, we can see a lot more stars very sharply. And so if you take these images over the years, you will notice that these stars, they actually move. And so if you take these images over the years, you will notice that these stars, they actually move. This is over the course of 15 years, we could follow the orbit of the stars. So they move about something that we can't see. And that thing is the black hole, the supermassive black hole at the center of our galaxy, which is basically 4 million times as massive as our sun. Now, you may have heard of very recent development in astronomy is that now we can actually see supermassive black holes. Sorry, still we can't see the black hole, but we can directly see the gas that moves around them at the very center. So, that was possible using a set of radio telescopes all around the world that work together to provide an incredibly sharp image for the at the very center of one very massive galaxy in the Virgo constellation. So let me now show you this movie with some sound.
I can't see the black hole.
You can't see the black hole. No, what you can see here is, yes, this is the black hole in the center, and around here what you see is the hot gas that moves around it. But you see, that's kind of a donut. The hot gas does not go into the black hole. I mean, actually does go into the black hole, but you cannot see the gas once it's in the black hole. So that tells you the size of this black hole, which is really cool.
But why do the black hole eat everything that goes close to it?
Well, I will explain this. I actually have explained this before. But anyway, yes, the result is that we can see how big is the black hole. And if you remember, bigger black hole, okay, means that they are more massive. Small black hole, they are small, they have less massive. And so just by measuring the size of a black hole, we can measure now their mass. Okay. Now, I'm moving closer to the end of this story, and I want to tell you something amazing about supermassive black holes. And that apparently big black holes live in big galaxies and small black hole lives in small galaxies. It is as if the black holes know in which galaxy they need to live. As it turns out, what this graph is showing you is a very tight relation between the mass of a galaxy, in this case it's in unit of times of Milky Way mass. Okay, so these guys up here on the right, they are 100 times more massive than the Milky Way. And whereas here at 1 we actually have the Milky Way in this graph, and the Milky Way has a black hole that, as I said, is around 4 million times the mass of the sun. So the black hole mass is here on this graph is in million times the sun of the sun times the sun of the sun. And you know, big galaxies here have black holes that actually are 1 billion solar masses. So here is the Milky Way again, and here is M87, the galaxy I was showing you before. Now, this is kind of puzzling because black holes Supermassive black holes, yes, they're quite, massive, but yet they're not as big as their galaxies. And yes, the supermassive black holes can have the size of, the entire solar system, but that's quite small compared to the Milky Way. So my line to you is, what's the radius of the supermassive black hole in the Milky Way? We know it is roughly the size of the solar system, but is this 100 times smaller than the Milky Way? 1,000 times smaller? A million times smaller, Morgana? Or 1 billion times smaller? What do you think?
A billion.
Yeah, it's 1 billion times smaller, which is really surprising. So how come that we have black holes that know in which galaxy they live when really they are so tiny compared to the galaxy? I mean, how is this possible? How is this possible that both the galaxy and the black hole, in a sense, grew together to really arrive at that precise relation between the mass of the galaxy and the mass of the black hole, which essentially tells you that the black hole is 0.2% the mass of the galaxy, when the black hole really is so tiny and insignificant compared to the galaxy? Well, we don't know. That's the answer yet. I mean, we have some ideas, but I like to put forward an analogy that because 1 billion times smaller is also the relative size of our molecule compared to that of our body. Okay, so I will say that the supermassive black hole could be like the DNA of galaxies. And the thing that is very puzzling is that, yes, that could be a suggestion, but how could it be? Very different galaxies out there. There are round galaxies, there are flat galaxies, there are galaxies that are red because they only have old stars, there are galaxies that have blue young stars. How could different galaxies share the same supermassive black hole budget? Okay, so how could they have the same fraction of black hole mass? And that's still an unanswered question, and I will now stop and take your questions on the chat. So good evening to everyone anyway.
So that concludes our very first Startracker online. I hope that you've enjoyed it and that you will look for some of those objects in the night sky. Definitely look out for Venus. It is absolutely spectacular at the moment. Now I might go out and do some stargazing myself, but Mark and Martina, they will be available to answer any questions that you might have over the next 10 to 15 minutes. Now once this live video ends, the video will be uploaded onto our Facebook page. Just pop your question into the chat box and Mark and Martina will be able to get back to you. So as I said, thank you very much for joining us. Have a lovely evening and stay safe.